We're now going to discuss a very important concept, particularly when we're about to do some calculus, of what a limit is. Now, a limit, we write it, it's got its own way of setting it out. So this is saying the limit as x approaches a of f of x. So given that we've got a function, what's the value of this function as x gets close to a particular value? In this case, x gets closer to a. Can we work out what that function will be as x gets close to a? Now, when we say it gets close to a, it doesn't actually equal a, but it gets so close to a that the value of the function would be the same as if x is equal to a. All right, so it approaches a. This says x approaches a, so it gets so close to a that it's just about equal to a. And there are three categories of limits. We're interested in particular values as x approaches particular values of the function. We're looking as x approaches 0. That's a special sort of category. And as x approaches infinity, as in other words, x gets larger, or x approaches minus infinity. So let's just look at these three different types of limits. So the limit as x approaches a particular value. So here we've got a function. Here's my function of x, 2x plus 4. And we want to know, does this function approach a particular value as x gets very, very, very close to 3? Now, the way to calculate the limit is simply, if you can just substitute it in, then you can substitute in and that will be the limit. Here we've got x approaches 3. There's nothing to stop us here from just substituting in x equals 3. So we just go 2 times 3 plus 4, and that is equal to 10. So the limit as x approaches 3 of 2x plus 4 is 10. You may recall that if we were to sketch y equals 2x plus 4, we would get quite a steep graph. And we want to know what would be the value at x equals, as x approaches 3. Now, as x gets either side of 3, it's going to be very, very close to 10. You can actually put values like 2.999 on your calculator and 3.001, and you'll find that the values are very, very close to 10 when you substitute it in. So that's a straightforward one. If you can substitute the value in and not have any problems, well, that's all good. You just substitute in and find the limit. If we've got something like this, and we substitute in, we get 3 squared minus 9 over 3 minus 3, which is a 0 on 0, which we cannot do. So we can't just do a substitution in. So what we've got to do is to try and figure out some way to find the limit of this function as x approaches 3. Another way of looking at it is this function is not defined for x equals 3. It would have a hole in the graph. If we were to graph this, there would be a hole in the graph at x equals 3. So it is not continuous. It has a hole at x equals 3. There's no value of the function when x equals 3. But as mathematicians, we're interested in seeing what happens if x gets really close to 3. Does it approach a particular value? Well, one way to do that is to try and see if we can factorize this and cancel it down. Now, until we actually put x equals 3 into this, we've got to keep writing limit. So we write limit as x approaches 3. Yes, we can factorize the top. It's the difference of two squares. So it is x minus 3. X plus 3 over x minus 3. Now we can see we can cancel down. And you keep writing limit until you actually do the substitution of x equals 3. So the limit as x approaches 3, this will cancel with that one of x plus 3. Now we don't have this problem of divisibility by 0. So now we can actually do the straight substitution, and we can say, right, now we can put x equals 3 in there, and that's equal to 6. 3 plus 3 is 6, so we don't write limit there anymore. So what we're saying is that as x gets really close to 3, this function, x squared minus 9 over x minus 3, will approach the value 6. Now, if you were to put in some tables of values and graph this, you will find that it is a straight line. This graph, even though you've got an x squared there, and you think, well, x squared's a parabola, when you've got something like that, it is a straight line, and it goes something like that. Now, it's not exactly like that. There is a small hole in the graph when x is equal to 3. And lo and behold, that will be the value of 6. And if you put x equals 2.9999 on your calculator into this, and you'll find that you'll get 5.9999 something. And if you put a value of 3 just greater than 3, 3.0001 in there, and calculate, you'll get 6.0001. So you can see that as you come from that side and as you come from that side, you are approaching the value 6. And so the limit of this function, even though it's not defined, so this is the graph of x squared minus 9 over x minus 3, so that's equal to f of x. Even though it is not defined for x equals 3, you can still find the limit. Okay, let's have a look at this particular case, and this is just a particular case of the limit as x approaches 0 of 1 on x. Now, once again, we can't just do a substitution like we did over here, because we get 1 over 0 and divisibility by 0 is undefined, so we can't work anything out there. So what we need to do here is we need to see what's happening on either side of 0. So to do that, if we want to see what's happening from the left, we go the limit as x approaches 0, and that up there means from the negative side. So we're coming in from the left of 1 on x equals, the way to work this out is to just put a value of x in here that is just very close to 0, but on the left hand side or on the negative side. That's what that negative up there means. So we could put negative 0.00001. So 0.401, negative that. Put it in there, and you'll find that you get a negative number that has a magnitude of quite large, like it'd be negative 100,000 or something like that. So as you get x closer and closer to 0 from the left-hand side, it approaches minus infinity. And if you approach 0 from the positive side of 1 on x, so we put 0.00001 in there, we'll find that it approaches positive infinity. Now, because we approach different values on either side, so here we're approaching negative infinity, here we're approaching positive infinity, therefore no limit at x equals 0. So we don't have a limit at x equals 0. That is, the limit as x approaches 0 of 1 on x does not exist. So these two values, if you approach the given value, and it applies to these values down here too, if you approach from the left and approach from the right and you get a different value, then there will be no limit. Now, if you were to sketch y equals 1 on x, you would get what's called a rectangular hyperbola, which looks like that. Here's my 0. So we're approaching 0 from this side. You can see that the value of the function goes all the way. It never cut the y-axis, but it'll keep on going down there, and the y value will get smaller and smaller and smaller. If we approach from this side, we get a bigger value for y, which is 1 on x, so it gets bigger up there. So here the y is approaching positive infinity. Down here it approaches minus infinity. And you can see that this has no limit. So that's when x approaches 0. The third option here is that x approaches infinity. Now, if you can just put in a large number, you can see that as x gets large, well, x squared is going to get even larger, and then it's 3. So you're going to get very large number as x gets larger, so it's just going to be equal to positive infinity. Incidentally, the limit as x approaches minus infinity of 3x squared, now because you square a negative number, that's going to be positive, that's also infinity. And comes as no shock that 3x squared, x squared is just a parabola, the 3 makes it even steeper. So as x gets bigger out this way, well, you can see that y, which is 3x squared, it's going to get bigger. And as x approaches minus infinity, which means as x goes out this way, that the function y is going to get to positive infinity as well. Okay, now here's another type of example that we tend to come across, and we've got two functions here with a power of x squared. If we've got this scenario, we take the highest power of x that's common top and bottom out. In this case, there's an x squared top and bottom, so we write limit as x approaches infinity. We factorise, we take x squared outside of something, and we take the same factor because there are x squareds top and bottom, we take them out. What are we going to multiply x squared by to get 2x squared? Well, that'll be 2 minus, what have we got to multiply x squared by to get x? It'll be 1 on x. So that's 2 minus 1 on x over x squared taken out the front, 3 plus 1 on x squared equals, the x squareds will cancel, so I'll just write that without the x squareds. X approaches infinity of 2 minus 1 on x over 3 plus 1 on x squared. Now, as we make x large, this is the reason we do this, as we make x large, 1 on x is going to approach 0. If you put x equals 1,000, x equals 1,000,000, 1 over 1,000,000 is very close to 0. Infinity is much bigger than 1,000,000. So 1 on a very large number is going to, so this is going to go to 0, and that's going to go to 0. So we'll get, now that we're putting this infinity value in here, we stop writing limit, and we write 2 minus 0 over 3 plus 0, which is 2 over 3. So as x gets very, very large, this function here approaches the value of 2/3. So that's how we do those. That's the concept of a limit. It's to find the value of a function as x gets very, very close to a particular value. We looked at x equals a particular value, x equals 0, x equals infinity. We've seen here that not all limits exist, that if you're after a particular one, you can approach that value from the left, approach it from the right. They must approach the same limit for the limit to exist. If they approach different values as 1 on x, then no limit exists.